The logical instructions that we're going to discuss in this lecture, you're not going to see them very often in programs, but because you might, I felt compelled to include a project for them in the manual and to discuss them. The person that's troubleshooting a PLC program has less latitude than someone that's writing it. If you're writing a PLC program, as long as it works when you're done, you can write it any way you want. No one's going to know the difference. You commission the project, the machine runs, makes product, everybody's happy, and off you go. The engineer, the person that commissions it. And I've commissioned hundreds of processes and machines. That doesn't mean that anybody did anything wrong, but the person who writes the program has the leeway or the latitude to use whatever instructions they want, whatever style they want. However, the person that's troubleshooting the program doesn't have a choice. You're handed a book and you read it the way it's written. So we try to include instructions that we know you're not going to see very often, which makes it just that much more important that you've at least seen them once before you're faced with it in the field. So let's go over this project for the bitwise, logical, and OR instructions. This is really a simple instruction, the bitwise AND. You can see in the top rung there that I have that rung enabled true. I'm going to toggle that off. And you see that I'm ANDing of interest and of interest. So these are two values of interest. Now I'm displaying them as binary because it is a bitwise AND. The AND logical function says if A and B are 1, then the destination is 1. 1 and 0 is 0, 0 and 1 is 0, but 1 and 1 is 1, logically. So if you want to compare two values and have a result that's based on the bits ANDed together, this is the instruction used. I don't really see an application where I would use it. I can describe one for you. Picture a rotary index table. Now, if you don't know what a rotary index table is, you're dead in the water on this illustration right off the bat. But a rotary index table is used in manufacturing where you load the base or the substrate for a part, and then the table indexes and moves the part to the next station, and all the stations are in a circle around the rotary index table. Let's say that the rotary index table has 12 locations or detents, which means every time it rotates 30 degrees, and then stops. So around the index table, the first position would be where you load the base for the part. Then you hit the palm buttons and it rotates 30 degrees, and the part that you just loaded rotates 30 degrees, usually to your right, but it could be in either direction, doesn't matter. Just depends on how you set it up. And then when the table stops, the station right next to you does something to the base, the unit base that you just loaded. It might come down and snap in a part. And then you load in another base right in front of you, the load station, and you hit the palm buttons and it indexes again. So the first part that you loaded that just had a part put in it, it rotates to the next station, and the part you just put in rotates again to the one right next to you, and it snaps another part. You could look at these the first 12 bits of source A and B as the status of the base as it goes around the index table. You could actually have a number of words, and if a certain function has been done to that part, and then as it rotates, the status moves to a more significant bit in the word that you're looking at here. If you arrived at station 5 and each of these two words had a 1, that would mean that it was a good part and it was ready to have the next part added. If it was a bad part, then its bit would be 0 and the logical result would be 0, and it would not put good parts after bad. So, imagine you've got a sub-base or a base, and it's going to have 10 operations on it. Well, if one of the operations fails, and now it's declared a bad part, you don't want to keep putting parts into that unit that is going to be rejected. So you would kind of push bits, and that might remind you of the bit shift left, bit shift right that we did. But you might want to AND the two status words together to get some sort of a result. And there's really hardly anything here to look at. Let's change some more of these to 1s. And we'll change one of these to 0. And so you keep an eye, and we'll make this one a 0. Okay, so if you look here, these are the only place where you've got 1 and 1 is here, and here, and here. So when we turn on input 0, you see that the result doesn't match either one of these two words. The result is any place where there's a 1 in both words, there's a 1 here. So if this and this, then that. If this and this, then that. If this and not this, then not. See? So down here we have, we're displaying those three values up here. We're displaying it here in integer. So I'm not going to labor this any further. The bitwise logical AND instruction, it's real simple, and there are people that use it. That's why I included it in the manual, but I don't want to belabor it. For those of you that needed a hard sell, I had you add this logic as well. And I'm showing that the exact same thing, only bit by bit. So you see here, of interest and of interest, I'm doing it by the bit. I mean, this works exactly the same way as that instruction does, but this is doing it the hard way. So you see any place that the matching bit between of interest and of interest, if they're both 1, then the logical result is 1. So this was for the folks that were a hard sell. This lab specifically was spotlighting the OR, bitwise inclusive OR. There's also exclusive OR. We won't talk about that right now. We're talking just about the bitwise and the bitwise OR. Inclusive includes either or. So with the AND, you're comparing bit by bit two words, two integers, bit by bit. You compare bit 0 with bit 0, bit 1 with bit 1, and so forth. If they're both 1, then the result is 1. If they're both 0, the result is 0. If either one is 0, the result is 0. Only if they are both 1 is the result 1. And you can see that I have the AND instruction activated. I'll toggle that off. And of course, it's not executing now, but the last thing that these bits heard was the execution from the AND. So they're still showing the logical result for ANDing these two groups of 32 bits against each other. The OR instruction will put a 1 in the result if either or both are 1. So I just activated or allowed this instruction to execute, and notice that the first 4 here, they're both 1. It puts a 1 down there, and here either one is 1, so it puts a 1 down here. And just to clarify that, I'll make this one a 0. And when I hit enter, watch this bit right here. See, it's now 0. If I make this one 1. Now it's 1 again. It doesn't matter which one of these is 1. If either of them or both, it's really either this one or this one will affect this one. That's where the OR comes in. Inclusive means it includes the case where they're both 1. The exclusive OR, it would only set the destination bit to 1 if one or the other were 1 but not both. So in this case right here, if this were exclusive OR, these 4 right here would all be zeros because it's exclusively not inclusive. That's enough said about the OR instruction. They're really straightforward. Again, the only examples I can think of for using them would be a rotary index table where you're using the bits to represent the some status for that station. Remember I described you've got 12 stations. Station 1, or if you want to call it 0, so it matches bit 0. You load a substrate or a base for an assembly in at station 0. You hit the palm buttons, it rotates 30 degrees, and it carries a 1 with it saying that there is a part installed there. So that right there is a use for shifting a 1 through, would be to represent whether there is or is not a part there. You certainly wouldn't want to come down with a fixture and install a part into the base if there's no base there. And then you could have 10 double integers, and each one represents some status on that particular nest in the rotary index table. That's the only example I can think of. For the real diehard, we had a little lab project in the manual that allowed you to exercise the OR concept or logic in its rawest form, and that is without an instruction, but you're actually comparing the same bits that you were comparing in the instruction, but in this case we're only comparing the first 5, bit 0 through bit 4. And we had an enable logic button. Once that was enabled and this was true, then any of these, if either one of these pairs here, if either bit in the pairs is true, then the output was true. And we also illustrated it didn't matter which one or if both. That was for the diehard. We've also got exclusive OR. In the next lab project, we have all 3 instructions: the AND, the bitwise AND, the bitwise inclusive OR, and the bitwise exclusive OR. And this is obviously the best way to compare these, is to take source A and source B, of interest and of interest, and see how what the AND, the bitwise AND does for a result in the destination, what the bitwise inclusive OR does to the value that ends up in the destination, and then of course the exclusive OR. And I think I have one more down here where I can move. First I'm going to AND it, and this is the exact same 2 values we had before, and you can see only the first 4 bits are both 1s, therefore the result is 1. We'll toggle that off. Now we'll OR it. And all 16 bits are on because source A is all 16 bits. Properly compare it. Now notice that I have a 0 in here for exclusive OR of interest. And I think I'm going to change this to binary as well, and put the same value in here that I had AND of interest there. Now I'm going to disable the OR and do the exclusive OR. So watch these 16 bits right here when we enable this instruction. See, the first 4 went to 0 because these are not exclusively OR. They're inclusively OR. So if we disable this and go back up here, now you'll see these 4 are now on, because the OR instruction is A or B or A and B, whereas the exclusive OR is A or B but not A and B. It's that simple. And then of course for the die-hard, we had some logic that allowed you to do it the hard way, so to speak, with straight logic. A and not B. In other words, if source A and not source B, then turn this on. If not source A but source B, then turn this bit on. So this is exclusively OR. And here we show you where we have one on and the other off. Remember, this is true if off. And then down below we show a combination here where we have both of these are on. In other words, these are true if off. Okay, I'm sorry, both of these are off. Here we have one on and one off, and here we have both on. So bit 2 of both of those, you know, source A and source B, there's 1, and we get a logical result of 0. So this little extra lab was just for the die-hard. Swap byte. Now I have used this instruction myself, and we've added it down here at the bottom, and we're using the exact same values. And the reason we did this way in the lab is so you could compare all of these instructions, and the swap byte is not the last one. We ANDed it to get a value in there. You know, I uploaded this and I see that I've got an input on it now. So I'm going to turn off 0, and I have values in here. So here's what I want you to look at. You have 16 bits that are 1 and 16 that are 0. So I'm going to turn on input 3, and notice what it did. It swapped the lower 16 bits for the upper 16 bits. So whatever is here at bit 0, and I'll change that, is now at this position. So we'll change that back and change this. So you see that it swapped the lower 16 for the upper 16, and it flipped the bytes, because remember, this is swap byte, not word. So a byte is 8 bits. So not only does it swap these 8 into the position of these 8, but it moves all 16 into the upper, well, if you want to call it integer, of a double integer. Now if you were working with integers instead of double integers, you would get a different result. Okay, just for grins, I added a rung. So this was our swap byte up here, and we're in the reverse mode. There's actually several different modes, order modes, and you can go explore those on your own. Keep in mind, if you want to swap the position of bytes, there's 4 bytes here. 8 bits is a byte, so that's the first byte, second byte, third byte, and fourth byte. If you want to swap bytes of data around within a word, an integer, double integer, then you want to use the swap byte instruction. So that's how this one worked in the reverse mode using double integers. So I created another rung of logic, and I took of interest and of interest, and I moved them into another register that was of interest integer. In other words, kind of the same name, but I put int on the end so you would know that it's an integer. You see, it's just 16 bits. Okay, so I took those two and I moved them in here, then I swapped those. Now the logical result is really what we wanted to flip. I created these as integers so you could see if you're only working with 16 bits, it only has one place to go, and that is, you see these, the least significant byte is all ones, and the most significant has a 0, and you see in the result that this byte has been moved to here and this byte to here. You swap the bytes. Just to clarify that, that's a little bit more explicit there. You can see that this nibble, if you want, or these 4 bits are now here and these 4 bits are now here. There's some uses for this. One of the places that I've used it is if I wanted to combine 2 groups of 8 bits from 2 different sources. I would take and swap the least significant byte to the upper, and then I would sum it with OR it, logically bitwise OR it, with another word that the lower byte was a value. So what you would end up with a result is 16 bits, and the first 8 bits, the first byte was from one word, and the upper byte was the lower byte from a different word. I'm sure that confused you. I probably didn't say that very good, but the lab explained it pretty well. Not to overlook it, but the NOT instruction, you could call that, almost call it invert if you want. We won't say negate because that's a whole different story, but a NOT instruction says if the source is not 0, then the result is 1. That's simple. Look at the bit pattern. Bit for bit, whatever the source is, the destination is exactly the opposite. And that is all there is to the NOT instruction. The bit fill distribute is actually a very handy instruction if you want to move a bit or group of bits to a different location in the destination. So our source could be any, in this case we're using double integers, it could be any double integer, but in this case we've got of interest, and that was our source A in all the other instructions, and then our logical result would be the result of this operation. Now if you look at the configuration, you've got 2 double integers, of interest and logical result, but you've got 4 other things there that are very important. The one is the source bit. The source bit is 4. That's not the 4th bit, but that is bit 4. So 0, 1, 2, 3, 4. So that would be this bit right here. That would be the 4th bit. And then the destination bit is bit 20. So this is 15, 16, 17, 18, 19, 20. So that would be bit 20 right there. And notice it says a length of 4. So this bit fill distribute will take, starting at bit 4, a length of 4 bits, and move it to 20, 21, 22, and 23. So I'm going to flip that switch, and you see that's exactly what it does. That's 20, 21, 22, and 23. So it moved these 4 bits right here up to this position. Now if we really wanted to emphasize that, okay, you see I've changed the value of this double integer, and I have just 1 bit on. So remember, this is going to start at bit 4, and it's going to take 4, 5, 6, and 7 and move it up into 20, 21, 22, and 23. Watch. So you see it moved these 4 bits up into these 4 bits. That's all the bit fill distribute does. Our just for fun number 8 gives us a chance to use the bit fill distribute instruction to shift, if you like, or move the 3 input bits from the 3 proxies. So the 3 proximity switches are going to be inputs 3, 4, and 5. However, if we were to use those 3 bits, that would give you a value much higher than what we want. We actually want those 3 bits, if they're all on, to be a 7. So to do that, we're going to take and we move the input bits into this word, and then this word, the source here, starting with bit 3, which would be input 3, we're going to move it backwards to bit 0, a length of 3. So you're going to move 3, 4, and 5 to 0, 1, and 2. Now right now we have all 3 of those on. All 3 inputs are on. So I'm going to pulse input 0, and you see we have a value of 7. So it has shifted. And of course the tray ID, I could show that in binary. So you can see it took these 3 right here and shifted them to here. Now to further illustrate that, I will take and put that back at 0, put that back at 0, and I will only turn on 2. So instead of having 3, 4, and 5 on, I'll just have 4 and 5 on. Pulse at 0, and you see that we had 7 last time. Now I'm displaying this in binary, so I'll put it back to decimal. Whoops. And you can see that we've got an ID of 6. So remember, this is the 1s, 2s, and 4s. So 2 plus 4 is 6. And that's all there is to the bit fill distributor.